Module 8, Dose Optimization, Quality Assurance. Take time to look at the learning outcomes for this module. In terms of knowledge and understanding, we hope that you will have an understanding of the basic principles behind the common parameters that are measured in cone beam CT quality assurance procedures. We hope that you will have an understanding of quality control test tools and phantoms, and that you will have a knowledge about the common problems with device performance and how this can be reflected on dose measurements or image quality. In terms of skills and abilities, you should be able to spot aberrations on dose or tube output measurements, and you should be able to detect changes in image quality when comparing to a normal image. Overall, the judgment and stance for this module is that we are striving for optimal CBCT scanner performance and image quality through quality assurance procedures. Council Directive 97/43 Euratom, the Medical Exposures Directive from the European Commission, states that all doses due to medical exposure for radiological purposes shall be kept as low as reasonably achievable, consistent with obtaining the required diagnostic information, taking into account economic and social factors. Furthermore, the directive states that the optimization process shall include the selection of equipment, the consistent production of adequate diagnostic information or therapeutic outcome, as well as the practical aspects, quality assurance, including quality control, and the assessment and evaluation of patient doses or administered activities, taking into account economic and social factors. Quality in radiology is of obvious importance. Poor quality radiological practices can lead to less effective diagnosis, repeat X-ray examinations, and excessive radiation doses to patients. Radiological quality assurance, also known as QA, can be defined as all those planned and systematic actions necessary to provide adequate confidence that a structure, system, component, or procedure will perform satisfactorily, complying with agreed standards. Quality control is part of quality assurance, the set of operations intended to maintain or to improve quality. It covers monitoring, evaluation, and maintenance at required levels of all characteristics of performance of equipment that can be defined, measured, and controlled. A radiological quality assurance program is the framework or organized effort which is devised to achieve quality assurance. It includes quality control, but also the administrative procedures to verify that the quality control techniques are performed properly and according to a planned timetable, that the results of these techniques are evaluated promptly and accurately, and that the necessary corrective measures are taken in response to these results. Looking at quality assurance programs for cone beam CT in dentistry, we can divide this up into 6 components: performance of the X-ray tube and generator, or X-ray equipment performance, quantitative assessment of image quality, display screen performance, patient dose assessment, clinical image quality assessment, and clinical audit. We'll look at each of these in turn. First of all, performance of the X-ray tube and generator. A program of testing X-ray equipment performance is a requirement of the European Union Medical Exposures Directive. It consists of a critical examination, acceptance and commissioning testing, and routine testing. For all these components, the advice of a medical physics expert is either essential or desirable. The critical examination of a cone beam CT installation is required to ensure that all safety features are correctly installed and functioning, and that adequate protection is provided to the operator and anyone else who may be in the area. For this, advice of a medical physics expert is valuable. In terms of acceptance and commissioning testing, this is about testing equipment performance parameters. It gives us baseline values for future routine tests, and it allows us to verify how the systems are pre-programmed for use in practice, and these tests are usually performed by a medical physics expert. Let's look at each of the tests in turn and briefly give you an understanding of what's involved. The first of these is X-ray tube output. This is simply trying to assess the quantity of X-rays that are produced for a particular exposure. It assesses the repeatability and the reproducibility of X-ray tube output. This is done using an ionization chamber, such as is shown on the picture here. The accuracy, repeatability, and reproducibility of kilovoltage is also assessed as part of acceptance and commissioning testing. This is the piece of equipment that might be used for this purpose. Again, this equipment would never be readily available to a dentist, so the involvement of a medical physics expert is essential. In terms of filtration, an initial acceptance or commissioning test will look at the amount of filtration on the machine. This can be estimated by measuring the half-value layer. What this means is the thickness of aluminium that is required to reduce the intensity of the X-ray beam by half. In very simple terms, if we consider the X-ray source and the detector, we can measure the X-rays hitting the detector using an ionization chamber when we expose it. Pieces of aluminium of varying thicknesses are placed between the X-ray source and detector, and the amount of aluminium required to reduce the intensity of the X-rays by half is used to interpret the actual filtration on the X-ray machine. In terms of radiation field of view, it's obvious that we need to be sure that the field size that is stated on the equipment is in fact correct, so that the testing confirms this and also confirms that the alignment is in accordance with the manufacturer's nominal field of view. Clearly, if there's a discrepancy in this, it may lead to rejected examinations due to missing off areas of interest, or alternatively overexposure of the patient where the field of view is actually bigger than the nominal field of view. Finally, leakage of X-rays. What we mean by this is the emission of X-rays in directions other than that we need to produce the image. Clearly this would be undesirable in terms of operator and staff protection. To do this, the exit portal of X-rays from the tube head is covered up by X-ray absorbent material, and detectors are placed at various positions around the X-ray source in order to detect X-rays being emitted in other directions. Finally, routine testing. The tests that have been conducted as part of acceptance and commissioning testing need to be repeated at regular intervals, and these tests would normally be performed by a medical physics expert. National requirements may dictate a specific frequency for these tests, but typically these should be performed on an annual basis. Let's move on to quantitative assessment of image quality. This requires the use of a QA phantom, which is basically a test object which we can expose to produce images which can be assessed in an objective way. This may be supplied by the equipment manufacturer when you buy a cone beam CT piece of equipment, but it may not in some instances. Other phantoms are commercially available. This includes the phantom produced by Leeds Test Objects Limited and developed as part of the Sydentex CT project. Phantoms for conventional CT equipment are not ideal for cone beam CT quality assurance processes. In terms of the Sydentex CT phantom, the design of this is a polymethyl methacrylate cylinder into which can be placed various inserts. These inserts are used to make specific tests of image quality. The whole phantom can then be scanned in a cone beam CT scanner, such as shown here. Analysis of the images of the test inserts involves both objective measurement and some subjective visual evaluation. In terms of the objective analysis, this can be performed using dedicated software tools. The software should be able to offer feedback to the user in form of acceptable ranges rather than absolute values. The following are some of the measurements that should be performed using a quality control phantom. These include image density values, contrast detail, uniformity and artifacts, image noise, spatial resolution, and geometric accuracy. We'll give you a rough outline of how these are performed. In terms of image density values, this uses an insert which is homogeneous, and what we do is measure the mean and standard deviations of pixel grayscale values in a specified region of the insert. Contrast detail measurements test a system's ability to display details of known varying contrast. In the photograph on the bottom right of the screen, you'll be able to see an example image from a phantom where we're doing contrast detail assessment. Here you can see the results of a contrast detail assessment from two different scanners. As you can see, there's a very big difference in the appearance of the images of the inserts, that the scanner on the right is giving far superior images than the one on the left. Uniformity and artifacts are assessed using an insert which contains high-density material, which will produce artifacts. By placing these in the phantom and scanning it, you can see the degree and intensity of the artifacts which are produced. Image noise is assessed by imaging a uniform part of the phantom on homogeneous material, and noise is expressed in terms of standard deviation of gray levels within the regions of interest selected in test objects with uniform densities. Spatial resolution tests the ability of the system to resolve two objects placed closely to each other. In order to do this, the phantom inserts contain bar patterns of various spatial frequencies, as you can see on the photograph on the bottom right. The line pairs that you can see in the phantom are pairs of equal-sized bars, and these are usually made of lead. The frequency is useful because the objects closely spaced together mean high frequency, and the finest bar pattern that can be distinguished determines the highest spatial frequency for that particular scanner. These two images show the same pattern imaged by two different cone beam CT scanners. Clearly there's a world of difference in image quality between the two of them. Finally, geometric accuracy. This is of obvious importance in clinical practice, particularly where measurements are of great importance, such as in implant dentistry. Where quantitative test tools are available, we can measure the distances and angles across a variety of the objects within the phantom. On the Sidentex CT phantom, you can see an example assessment of geometric accuracy being made on the phantom image. One aspect of quality assurance in any form of radiology, which is frequently ignored, is display screen performance. We can produce beautiful images, but if we are viewing them on inadequate screens, then the quality that we observe will be less than ideal. Therefore, it's important to test the quality and condition of our display screens as part of a quality assurance program. To do this, a suitable test pattern, such as an AAPM or SMPTE image, should be installed on the computer and viewed on the monitor, which should of course be cleaned. These test patterns are easily downloadable from the internet. You should be checking that all distinct grayscale levels on the test pattern can be individually resolved. It should also be ensured that all of the bars on each of the resolution patterns on the test images can be clearly resolved. Let's move on to patient dose assessment now. You'll remember in modules 3 and 4 we learned about effective dose. This is the measure of dose that we can equate to risk. Unfortunately, this cannot be measured in vivo, so we need more easily measured dose quantities. There are 3 we need to think about. The first of these is CTDI, or the CT dose index. This is what is used normally for the assessment of patient dose in conventional medical CT scanning. It's the measurement of the dose integrated across the dose profile along the patient's length, and is measured using a pencil detector either in air or in a Perspex phantom. Unfortunately, CTDI is not ideal for cone beam CT equipment. However, some manufacturers do use this in their recommendations, in which case it would be appropriate to try to follow those recommendations. As part of the Sydentex CT project, an attempt was made to devise a CBCT dose index that was analogous to CTDI. And it is possible to devise a method such as this, taken from the quality control manual included in the Sydentex CT guidelines, in order to use a dose index for cone beam CT. However, there are difficulties associated with using a cone beam CT dose index because of the asymmetric positioning of field of views within the patient and the use of, for example, partial rotations of scanners. Consequently, most emphasis at the moment is being paid to the concept of dose area product, or DAP. Dose area product is, as its name suggests, the product of the dose in the beam multiplied by the area of the beam at that point. In order to calculate this, we use a calibrated special ionization chamber that integrates the dose across the primary beam. This is called a DAP meter. The unit of DAP is milligrays centimeter squared, as suggested by its definition. This is the ideal method of auditing cone beam CT dose in dental practices and to set standards. Diagnostic reference levels of dose are dose levels in medical radiodiagnostic practices for typical examinations for groups of standard-sized patients, and these are derived from large audit samples in the field. Diagnostic reference levels are expected not to be exceeded for standard procedures when good and normal practice regarding diagnostic and technical performance is applied. In some aspects of dental practice, we are familiar with the concept of diagnostic reference levels. For example, here is a set of data from the Health Protection Agency in the UK, giving dose data for panoramic X-ray equipment. You'll notice if you look carefully that the unit here is not DAP but DWP, dose width product. This reflects the way in which panoramic equipment works, but nonetheless the information in the graph is useful because it shows us the wide range of radiation doses given in dental practice for the same X-ray examination. And this is a large audit survey. Using this data, it's possible to set a diagnostic reference level. This level represents the third quartile points. 3/4 of dentists, or dental X-ray equipment, lie below this level in terms of dose. The rationale behind this is that if 3/4 of dental practices can achieve doses lower than this level, the other quarter should be able to achieve it by optimization methods. Unfortunately, there is insufficient audit data on cone beam CT to set a formal DRL at the present time. Instead, an achievable dose has been set as a provisional measure. This is based upon cone beam CT of an adult patient being assessed for a single upper molar implant. In the Sidentex CT guidelines published in 2011, this states that until further audit data is published, the panel recommend the adoption of an achievable dose area product of 250 milligray centimeter squared for cone beam CT imaging for the placement of an upper first molar implant in a standard adult patient. In the future, an achievable dose and eventually a DRL should also be set for pediatric cone beam CT. Let's move on now to clinical image quality assessment. This is obviously something closer to the dentist rather than to a medical physics expert. The consistent production of adequate diagnostic information from radiological examinations is central to optimization. But there is a lot of research evidence that suggests that radiographic image quality is often less than ideal in primary dental care. The higher radiation doses of cone beam CT compared with conventional dental radiography mean that standards must be rigorously maintained. How then do we assess clinical image quality? Well, we do it all the time when we're viewing our images of patients. But one well-established method of doing this is to use reference images. This helps to guard against a gradual drift away from optimal quality which can occur in practice over time. In order to do this, we use a CBCT scan dataset of excellent quality, and this is used as a reference against which everyday clinical scans can be assessed. For example, here on the top right, we have a reference image, a reformatted image from a cone beam CT scan dataset. Obviously, if your clinical images and subsequent examination were beginning to change their image quality, such as the one on the bottom right here, then you would be aware that there was a problem and it needed to be corrected. However, in terms of clinical image quality assessment, what most people mean by this is audit against established clinical image quality criteria. In medical practice, there are several different publications on quality criteria for radiological images, as you see listed on the left. This includes European guidelines on quality criteria for computed tomography, conventional CT. Here are some example image quality criteria for examination of the paranasal sinuses. Unfortunately, there are no comparable established criteria for dental cone beam CT at the present time. Finally, let's look at clinical audit. In a sense, this is still part of clinical image quality assessment, but we choose to give it some prominence here because it is something very practical that the dentist with a dental cone beam CT scanner can do. Let's first define what clinical audit is. It's a quality improvement process that seeks to improve patient care and outcomes through systematic review of care against explicit criteria and the implementation of change. This is often shown diagrammatically, as shown here. Let's look at that in more detail. In clinical audit, it's important first of all to identify an issue. In our case, we're looking at cone beam CT clinical image quality. When we look at our images, some problems, such as the metal artifacts on this scan, are obvious, easily identified, and can be explained as isolated cases, or as things that we cannot do anything about. However, other problems can be insidious and become normal and begin to be ignored, and this is clearly not acceptable. Once we've identified the issue, in this case image quality, we need to set standards. The Sidentex CT project has set as a minimum target no greater than 5% of cone beam CT examinations as unacceptable. that is, examinations that do not satisfy the diagnostics for which they were taken. The aim of this should be to reduce the proportion of unacceptable examinations by 50% in each successive audit cycle. Here are some more detailed clinical quality standards for cone beam CT images, as taken from the Sedentex CT guidelines of 2011. This is helpful in performing a clinical audit as it gives us some reference information against which we can compare our own images. The next step is to observe practice and collect data. Now this can be prospective or retrospective. Unlike research, we do not need a very large sample size. 50 consecutive cone beam CT examinations will probably be enough to perform a clinical audit. We need a simple data collection pro forma, which records the examination identity details, an assessment of the acceptable and unacceptable status, and a record of any specific faults that we pick up. It's important that all clinical staff involved in cone beam CT should be involved. Audit should always be multidisciplinary and inclusive. What do we do next? Well, if we just revise what we've said, first of all, we've identified the issue, we've set the standards, we've observed practice and collected data. We compare our practice to the good practice guideline. If you find that you have greater than 5% of cone beam CT examinations classified as unacceptable, clearly you need to introduce some change or some action to try and improve things. Finally, we must re-audit at the end of this cycle. This is in order to see whether our changes or actions have been of benefit. So in conclusion, we've identified 6 components of the quality assurance program for cone beam CT in dentistry: the performance of the X-ray tube and generator, quantitative assessment of image quality, display screen performance, patient dose assessment, clinical image quality assessment, and clinical audit. From the Sedentex CT guidelines document of 2011, you can see the suggested frequency of different tests recommended in the quality assurance program, their priority levels, and the sort of expertise that's involved, whether these can be done in-house by the clinical staff or whether the advice or contribution of a medical physics expert is required. This table also shows action levels when something needs to be done if the equipment or the image quality falls outside the recommended levels. Take some time to go through this in detail. So in summary, we have defined what is meant by quality assurance and quality control and defined the components in a quality assurance program for cone beam CT. We have highlighted that much of this work cannot be performed directly by the dentist and that involvement of a medical physics expert is desirable or in some cases essential. Some efforts, however, such as clinical audit, can be performed without specialized equipment or knowledge, and dentists using cone beam CT should pay attention to these aspects. Please ensure that you complement this PowerPoint with additional materials, in particular by reading Section 6 of the Sedentex CT Guidelines and Appendix 1, the Quality Control Manual within the guidelines.